Look up at the night sky. What you see, the stars, the galaxies, the shimmering cosmic tapestry, is just a fraction of the story. What if I told you that everything visible, everything we've ever observed, makes up less than 5% of the universe? The rest is hidden in plain sight, an invisible force shaping the cosmos in ways we're only beginning to understand. This is dark matter, the universe's best-kept secret. It doesn't glow, it doesn't reflect, it doesn't interact with light at all. Yet without it, galaxies would fly apart, stars would scatter, and the universe as we know it wouldn't exist. Think about that for a second. The very fabric of reality is held together by something we can't even see. Over the next few minutes, we're going to pull back the curtain on this cosmic mystery. You'll discover how scientists hunt for the invisible, why dark matter might rewrite the laws of physics, and what it means for the future of our universe. Stick around, because what you don't see might just change everything you thought you knew. Now, let's break down the basics of this cosmic enigma. Dark matter is unlike anything you've ever touched or seen. It's a ghostly substance that doesn't shine, absorb, or reflect light. Imagine trying to spot a shadow in a pitch-black room. That's how elusive it is. Yet, despite being invisible, its gravity is undeniable. It tugs on stars, bends the paths of galaxies, and holds the universe together like an unseen scaffold. Here's the staggering part. While everything we can see, planets, stars, galaxies, makes up just 5% of the universe's total mass and energy, dark matter accounts for 27%. That's over 5 times more than all the visible matter combined. Think of it as the hidden framework of a building. You don't see the steel beams, but without them, the entire structure would collapse. In the cosmos, dark matter's gravitational pull is what gathered gas and dust into the first galaxies billions of years ago, shaping the universe into the web of stars and clusters we observe today. Without it, the night sky would be empty, and we wouldn't be here to ponder its mystery. So next time you gaze at the stars, remember, what's invisible is just as important as what's shining. Now, let's step back in time to uncover how this cosmic mystery first came to light. The story of dark matter begins in the early 20th century with a brilliant but often overlooked astronomer named Fritz Zwicky. In 1933, while studying the Coma Cluster, a massive group of galaxies, he noticed something bizarre. The galaxies were moving so fast that they should have flown apart, yet they stayed bound together. Zwicky calculated that the visible mass in the cluster wasn't nearly enough to hold it together with gravity. He called this discrepancy missing mass, and though his peers dismissed it at the time, he was the first to point a finger at the invisible glue we now call dark matter. Fast forward 4 decades, and another trailblazing scientist, Vera Rubin, took the baton. In the 1970s, she meticulously mapped the speeds of stars orbiting the centers of galaxies. What she found defied expectations. Instead of slowing down as they moved farther from the galactic core, as Newton's laws predicted, the stars maintained blistering speeds. The only explanation, an enormous amount of unseen matter, its gravity keeping those stars from flinging into the void. Rubin's work didn't just confirm Zwicky's hunch, it turned dark matter from a fringe idea into a cornerstone of modern astrophysics. These two visionaries, separated by time but united by curiosity, laid the groundwork for a revolution in our understanding of the universe. Their discoveries remind us that sometimes the most profound truths are hidden in plain sight, or in this case, in the absence of light. Now, let's turn our attention to one of the most compelling pieces of evidence for dark matter: its gravitational fingerprints scattered across the cosmos. Picture this: light traveling billions of light years from distant galaxies doesn't always move in a straight line. Instead, it bends, warped by the immense gravity of invisible dark matter, like a cosmic magnifying glass distorting the view behind it. This phenomenon is called gravitational lensing, and it's one of the clearest ways we detect the unseen. Take the bullet cluster, for example. This pair of colliding galaxy clusters is a smoking gun for dark matter. When astronomers observed it, they saw something extraordinary. The visible matter hot gas detected by X-rays had slowed down during the collision, like two clouds of smoke bumping into each other. But the mass, mapped by gravitational lensing, kept right on moving, unaffected. Why? Because the bulk of the mass wasn't in the gas, it was in the dark matter, which passed through the collision like a ghost. This mismatch between visible matter and gravitational pull was undeniable proof that something invisible was out there, shaping the universe. But gravitational lensing isn't just about dramatic collisions. It's everywhere. Dark matter's gravity acts like cosmic scaffolding, bending the light from background galaxies into arcs, rings, or even multiple images of the same object. By studying these distortions, astronomers can map the distribution of dark matter across the universe, revealing vast, invisible structures that guide where galaxies form and how they cluster together. So, while dark matter remains invisible to our telescopes, its gravitational grip leaves unmistakable marks on the fabric of space-time. It's like finding footprints in the sand. You might not see the creature that made them, but you know it's there, shaping the world around you in ways you can't ignore. And with every new observation, we get one step closer to unraveling the mystery of this hidden cosmic architect. Now, let's untangle another cosmic mystery, dark energy, and see how it stacks up against dark matter. While both are invisible and make up most of the universe, they play completely opposite roles. Think of dark matter as an invisible rope pulling galaxies together with its gravity, keeping them from flying apart. Without it, galaxies like our Milky Way would spin themselves into oblivion, stars scattering like marbles dropped on the floor. But dark energy, it's the universe's unstoppable wind, pushing everything apart, accelerating the expansion of space itself. Imagine blowing up a balloon with tiny dots on its surface. As the balloon inflates, the dots move away from each other, not because they're moving, but because the space between them stretches. That's dark energy at work, and it's why the universe isn't just expanding, it's doing so faster and faster. Here's the kicker: dark matter and dark energy aren't just different, they're locked in a cosmic tug of war. Dark matter's gravity tries to clump galaxies together, building the universe's structure, while dark energy fights to tear it all apart, stretching space-time thinner and thinner. Right now, dark energy is winning. Billions of years from now, if this keeps up, distant galaxies will vanish over the horizon, their light never reaching us again. So why does this matter? Because these two invisible forces shape everything. Dark matter builds the cosmic scaffolding, while dark energy decides the universe's ultimate fate. One pulls, the other pushes, and together they write the story of reality itself. Now, let's zoom in on one of the most promising suspects in the hunt for dark matter: weakly interacting massive particles, or WIMP for short. Picture these as cosmic ghosts, particles so elusive they barely interact with ordinary matter. Yet their sheer mass could explain why galaxies hold together the way they do. Scientists love WIMP because they fit neatly into existing physics, like a missing puzzle piece from the standard model. These particles are thought to be heavy, much heavier than protons, and they only interact through gravity and the weak nuclear force, the same force behind radioactive decay. That's why they're so hard to detect. Imagine trying to catch a shadow with your bare hands. That's the challenge physicists face. But here's the exciting part. If WIMP exist, they might occasionally bump into atomic nuclei here on Earth, leaving behind tiny flashes of energy. Experiments deep underground, shielded from cosmic noise, are listening for these whispers from the dark. Why are WIMP such a strong candidate? Because they naturally emerge from theories like supersymmetry, which predicts a whole family of yet-to-be-discovered particles. If WIMP are out there, they could solve two mysteries at once: dark matter and the gaps in our understanding of particle physics. It's like finding a key that unlocks two different doors. Of course, the hunt isn't over. Despite decades of searching, no one has definitively caught a WIMP yet. But the absence of evidence isn't evidence of absence. Every experiment that comes up empty-handed helps narrow the search, bringing us closer to the truth. Whether WIMP turn out to be the answer or not, their story is a testament to science's relentless curiosity and the universe's endless surprises. Next up, we'll explore another intriguing dark matter candidate, actions particles so light and strange they could rewrite the rules of the cosmic game. Now, let's turn our attention to a dark matter candidate that couldn't be more different from WIMP actions. Imagine a particle so light it barely has any mass at all, yet it could be the invisible glue holding galaxies together. Actions were first dreamed up by quantum physicists to solve a completely unrelated puzzle: why the universe doesn't seem to care if you flip left and right while also reversing time. But here's the twist. These ultra-light particles might also be the missing dark matter we've been searching for. Unlike WIMP, which are heavy and interact weakly, actions are featherweight and behave more like waves than particles. Picture a vast ocean of these tiny ripples flowing through space, gently tugging on galaxies with their collective gravity. Because they're so light, actions would exist in staggering numbers. Trillions could be passing through you every second without a trace. The hunt for actions is just as fascinating as the particles themselves. Experiments like the Action Dark Matter Experiment, or ADMX, use powerful magnetic fields to try and coax actions into revealing themselves. Think of it like tuning a cosmic radio. If actions are out there, they might convert into faint microwave signals under the right conditions. It's a delicate process, but one that could pay off with a discovery as revolutionary as finding dark matter itself. So how do actions stack up against WIMP? While WIMP rely on their sheer mass to explain dark matter, actions bank on their overwhelming numbers. It's the difference between a few heavy boulders and a mountain of sand. Both can weigh the same, but they behave in wildly different ways. And if actions are real, they'd open doors to new physics beyond even the standard model, hinting at hidden forces and dimensions we've yet to imagine. The beauty of science is that we don't have to choose just one theory. Whether it's WIMP, actions, or something even stranger, the search for dark matter is far from over. And with every experiment, we're peeling back another layer of the universe's deepest mysteries. Now, let's shift gears and talk about another intriguing idea scientists once considered: massive compact halo objects, or MACHO. These aren't exotic particles like WIMP or actions, but actual cosmic heavyweights: black holes, neutron stars, and even rogue planets drifting unseen through the galaxy. At one point, researchers thought these massive, invisible objects might be the hidden mass tugging on stars and galaxies. The logic was simple. If dark matter doesn't interact with light, maybe it's just ordinary matter that's too dim to see. Imagine a swarm of black holes lurking in the outskirts of galaxies, their gravity pulling on stars without emitting a single photon. It's a compelling idea, and in the 1990s, astronomers launched ambitious searches to find them. They used a clever trick called gravitational microlensing, waiting for a MACHO to pass in front of a distant star, bending its light and causing a temporary brightening. But here's the catch: after years of scanning the skies, the numbers just didn't add up. While some MACHO were detected, there weren't nearly enough to account for all the dark matter's gravitational effects. It turns out these objects are like scattered pebbles when we need an entire mountain. Even if every failed star and ancient black hole in the galaxy were counted, they'd only make up a tiny fraction of the missing mass. So why did MACHO fall short? For one, they're simply too rare. The universe doesn't produce enough black holes or neutron stars to match dark matter's overwhelming presence. Plus, their gravity would leave other traces, disrupting star clusters or warping galaxy shapes in ways we don't observe. In the end, MACHO became a fascinating dead end, teaching us that dark matter must be something far stranger than just hidden ordinary matter. This brings us back to the bigger picture. Dark matter isn't just hard to see, it's fundamentally unlike anything we've encountered before. And as we'll see next, that mystery only deepens when we look at the cutting-edge experiments hunting for it today. But if Macho couldn't solve the dark matter puzzle, where do scientists turn next? The answer lies deep underground, literally. Some of the most ambitious experiments hunting for dark matter are buried beneath layers of rock, far from the interference of cosmic rays and everyday radiation. Take the LUX Zeppelin experiment, for example. Nestled nearly 1 mile below the Black Hills of South Dakota, this ultra-sensitive detector is essentially a high-tech trap waiting for dark matter to bump into it. The setup is mind-boggling, a giant tank filled with liquid xenon chilled to extreme temperatures. If a dark matter particle like a WIMP passes through and collides with a xenon atom, it should produce a tiny flash of light and an electric signal. The surrounding rock acts like a natural shield, blocking out unwanted noise from the surface so scientists can focus on those rare, precious interactions. Then there's Xenon 1T, its counterpart buried under a mountain in Italy. Using similar technology, it holds the record for being one of the most sensitive dark matter detectors ever built. These experiments operate like cosmic listening posts, tuned to catch the faintest whispers of particles that otherwise ignore everything around them. Why go to such extremes? Because dark matter doesn't just avoid light, it barely interacts with ordinary matter at all. To have any hope of detecting it, scientists need near-perfect silence. Even a single stray radioactive atom in the detector could mimic a dark matter signal, sending researchers down the wrong path. That's why these labs are so meticulously clean, shielded, and buried. They're hunting for a ghost, and ghosts don't leave many footprints. So far, neither experiment has found definitive proof of dark matter, but that doesn't mean failure. Every null result helps narrow down the possibilities, ruling out certain types of particles and refining the search. And with next-generation detectors already in the works, the hunt is only getting more precise. Because if dark matter is down there somewhere in the quiet dark beneath our feet, we're getting closer to hearing its voice. And speaking of listening, the search doesn't stop underground. Some of the most creative dark matter hunters are looking up, scanning the cosmos for clues in places we'd least expect. While underground labs listen for whispers of dark matter, other scientists are scanning the skies for its cosmic fingerprints. High above Earth's atmosphere, space telescopes act as silent detectives, hunting for clues in the light we cannot see. One of the most powerful tools in this search is the Fermi Gamma Ray Space Telescope, a spacecraft designed to catch the universe's most energetic light, gamma rays. Here's why gamma rays matter in the dark matter hunt. Some theories suggest that when dark matter particles collide, they might annihilate each other, releasing bursts of gamma radiation. Fermi scans the skies, particularly the dense centers of galaxies where dark matter is thought to cluster, searching for these faint but telltale flashes. Imagine it like looking for the glow of a firefly in a vast, dark forest, except the firefly might be a particle that makes up most of the universe's mass. Another intriguing target is cosmic rays, high-energy particles racing through space. Some researchers believe dark matter could decay into these particles, leaving behind a trail we might detect. Experiments like the Alpha Magnetic Spectrometer, mounted on the International Space Station, sift through cosmic rays for anomalies that could point to dark matter's influence. So far, no definitive signal has been found, but every unusual gamma ray excess or unexplained cosmic ray spike sparks excitement. The absence of proof isn't proof of absence. It just means we're still learning where and how to look. And with new space missions being planned, the search is only getting sharper. Because if dark matter hides in the voids between stars, we now have the tools to chase its shadow across the cosmos. And speaking of shadows, some scientists are taking a different approach, not just looking for dark matter, but trying to create it ourselves. Now, let's take the search for dark matter from the vastness of space to the precision of Earth's most powerful machines. Enter the Large Hadron Collider, the world's largest and most energetic particle accelerator. Nestled underground near Geneva, this colossal ring, stretching over 16 miles, is where scientists smash protons together at nearly the speed of light. The goal, to recreate the extreme conditions of the early universe, and maybe, just maybe, produce dark matter particles in the process. Here's how it works. When protons collide at such incredible speeds, they release a burst of energy that can briefly form new particles. Some theories suggest dark matter could be among them, though these particles would instantly vanish, leaving no direct trace. Instead, scientists look for imbalances in the aftermath, missing energy or momentum that could hint at dark matter slipping away undetected. Think of it like a game of cosmic billiards. If the balls don't add up after a collision, something invisible might have carried off the extra energy. The LHC has already made history, like its discovery of the Higgs boson in 2012. But dark matter remains elusive. Despite countless collisions, no definitive signal has emerged. Yet this isn't a dead end. It's a process of elimination. Each null result helps narrow down the possibilities, refining our understanding of where dark matter might hide. And with upgrades boosting the collider's power, the hunt is far from over. What makes this approach unique is its boldness. Instead of waiting for dark matter to reveal itself naturally, we're trying to conjure it in a lab, testing the boundaries of known physics. Whether the LHC eventually uncovers dark matter or forces us to rethink our theories, one thing's certain: the answers we seek might be hiding in the debris of these microscopic explosions. And as the collider keeps pushing limits, the invisible universe feels just a little closer to being seen. Next, we'll explore how dark matter's gravitational pull doesn't just hide in particle detectors. It shapes the very structure of galaxies themselves. Now, let's step back in time to witness how dark matter laid the foundation for the galaxies we see today. Billions of years ago, the universe was a swirling sea of gas and energy, but something invisible was already at work: dark matter's gravity. Picture it as an unseen architect quietly shaping the cosmos long before stars or galaxies existed. One of the most groundbreaking tools to reveal this process is the Millennium Run, a supercomputer simulation that recreates the universe's evolution. By mapping dark matter's gravitational pull, scientists watched as it clumped together, forming a vast cosmic web. These dense knots of dark matter acted like gravitational anchors, pulling in clouds of hydrogen gas. Over eons, that gas collapsed under its own weight, igniting the first stars and birthing the earliest galaxies. What's fascinating is how dark matter's role wasn't just passive, it was transformative. Without its scaffolding, ordinary matter would have been too spread out to coalesce into galaxies. Think of it like a mold for a sculpture. Dark matter provided the structure, while gas and stars filled in the details. Simulations show that galaxies formed precisely where dark matter was densest, following its invisible blueprint. This process wasn't instant. It took hundreds of millions of years for gravity to work its magic, with dark matter's subtle tug gradually amplifying tiny fluctuations in the early universe. Those faint ripples grew into the sprawling galactic cities we observe today, from spirals like the Milky Way to massive elliptical galaxies. The takeaway: dark matter didn't just influence galaxy formation, it made it possible. Every star, every planet, even us, owe our existence to this mysterious substance weaving the universe together behind the scenes. And as simulations grow more advanced, they're revealing even more about how dark matter's hidden hand guided the cosmos from chaos to order. Next, we'll zoom in on our own galactic neighborhood to explore the Milky Way's dark halo, a vast, invisible cloak that keeps our galaxy intact. Now, let's turn our attention closer to home, our very own Milky Way. Imagine wrapping your arms around something invisible, something so massive it holds an entire galaxy together yet remains completely unseen. That's the Milky Way's dark halo, a vast spherical cloud of dark matter enveloping our galaxy like a ghostly embrace. This halo isn't just a faint wisp, it's colossal, stretching hundreds of thousands of light years beyond the Milky Way's glittering spiral arms. While the stars and gas we see make up only a fraction of the galaxy's mass, the dark halo accounts for nearly 90% of it. That means most of what holds our galaxy together isn't just hidden, it's downright dominant. So how does this invisible giant keep the Milky Way intact? Think of it like an anchor in a storm. The halo's immense gravity acts as a stabilizing force, preventing stars and gas from flying off into the void as the galaxy spins. Without it, the Milky Way would unravel, its stars scattering like leaves in the wind. Even our solar system, orbiting 26,000 light-years from the center, is held in place by the halo's relentless pull. But here's the twist: the dark halo isn't uniform. Recent studies suggest it's lumpy, with denser clumps of dark matter scattered throughout. These invisible knots might even leave subtle fingerprints on the motions of nearby stars, giving astronomers clues to map the unseen. The takeaway: our galaxy is far more than what meets the eye. The Milky Way's dazzling stars are just the glittering surface of a deeper, darker reality, one where an invisible halo silently dictates the rules of cosmic survival. And as we peer deeper into this mystery, we're reminded just how much of the universe remains hidden in plain sight. Next, we'll unravel another cosmic puzzle: why stars orbit galaxies at speeds that defy gravity's usual rules, a mystery that first hinted at dark matter's existence. Now, let's dive into one of the most compelling pieces of evidence for dark matter, something that first made scientists sit up and take notice. Picture a merry-go-round spinning faster than it should, defying the laws of physics as we know them. That's essentially what's happening with stars in galaxies, and it's called the galaxy rotation curve problem. Here's the mystery: when astronomers measured how fast stars orbit the center of galaxies, they expected the outer stars to move slower, just like planets farther from the sun orbit more sluggishly. But what they found was shocking. The outer stars were whipping around just as fast as the inner ones, as if some unseen hand was giving them an extra push. This shouldn't happen. Based on the visible matter, stars, gas, and dust, the gravity just isn't strong enough to keep those outer stars from flying off into space. So what's holding them in place? The answer, of course, is dark matter. Its invisible gravity acts like an extra anchor, providing the pull needed to keep those stars moving at breakneck speeds without escaping. To visualize this, imagine a galaxy as a city. The visible matter is the downtown area, bright and bustling, but the real power lies in the suburbs, where dark matter's gravity stretches far beyond the lights, keeping everything connected. Without it, the city's outskirts would crumble into chaos. This discovery, first made by astronomer Vera Rubin in the 1970s, was a game-changer. It showed that galaxies aren't just what we see, they're embedded in vast halos of dark matter, shaping their very motion. And it's not just our Milky Way. Every spiral galaxy we've studied shows this same bizarre behavior, proving dark matter isn't a fluke, it's fundamental. So next time you look up at the night sky, remember, the stars aren't just dancing to the tune of visible matter. They're moving to the rhythm of something far more mysterious, something we're still struggling to understand. And that brings us to the next piece of the puzzle: how dark matter weaves the universe itself into a vast, invisible web. Now let's pull back and see the bigger picture, because dark matter doesn't just shape individual galaxies. It sculpts the entire universe into an intricate cosmic web. Imagine the universe as a spider's silk stretching across unimaginable distances. But instead of dew droplets, galaxies cling to the intersections of these invisible threads, forming glittering nodes in a vast, dark framework. This web is woven by dark matter's gravity, After the Big Bang, tiny fluctuations in density gave dark matter a head start, pulling ordinary matter into its gravitational embrace. Over billions of years, these ripples grew into colossal filaments, rivers of invisible mass flowing through the cosmos. Where these rivers crossed, galaxies pooled like water in a basin, creating the dazzling clusters and superclusters we see today. Computer simulations like the famous Millennium Run reveal this structure in stunning detail. They show dark matter as the universe's scaffolding, a hidden skeleton that dictates where galaxies form and how they move. Without it, the cosmos would be a scattered, formless void. But here's the twist: this web isn't static. It's alive with motion, as dark matter's gravity tugs galaxies along filaments like beads on a string. Some are racing toward colossal intersections, future sites of galactic collisions. Others drift in quieter voids, isolated but still tethered to the web's pull. So when you gaze at a map of the universe, remember, you're not just seeing stars and galaxies, you're glimpsing the shadowy architecture of dark matter, the silent force that built the cosmos as we know it. And this revelation leads us to an even deeper mystery. Could dark matter also hold the key to the birth of black holes? Now, let's venture into one of the most intriguing puzzles in modern astrophysics, the mysterious relationship between dark matter and black holes. Could this invisible substance be the hidden fuel behind the growth of supermassive black holes, those monstrous giants lurking at the centers of galaxies? Scientists have long wondered how supermassive black holes grew so enormous so quickly in the early universe. Some propose that dark matter might have played a starring role. One hypothesis suggests that as dark matter particles collide and annihilate near black holes, they release energy, feeding the black hole's expansion. Another idea is that dark matter's gravity funnels ordinary matter into the black hole's grasp, acting like an invisible conveyor belt, but not all researchers agree. Some argue that dark matter's weak interactions make it a poor food source for black holes, pointing instead to gas and stars as the primary fuel. Others speculate that dark matter could form dense clumps around black holes, creating a gravitational boost that accelerates their growth. The debate gets even wilder when we consider primordial black holes, hypothetical black holes formed in the early universe. Could some of these be made entirely of dark matter? If so, they'd be invisible except for their gravity, blending seamlessly into the cosmic background. What's clear is that dark matter and black holes are tangled in a cosmic dance, each influencing the other in ways we're just beginning to unravel. And as we peer deeper into this mystery, we might uncover secrets that rewrite our understanding of both. This brings us to another radical idea. What if gravity itself behaves differently on cosmic scales? That's the bold claim of an alternative theory called modified Newtonian dynamics, and it's where we're headed next. Now, let's take a step into a completely different corner of the cosmic debate, one that challenges the very foundation of our understanding of gravity. Instead of invoking dark matter to explain the mysteries of galaxy rotation and cosmic structure, some scientists propose a radical alternative. What if gravity itself works differently on the vast scales of the universe? This idea is known as modified Newtonian dynamics, or MUND for short. MUND suggests that the force of gravity doesn't follow Newton's laws precisely when dealing with extremely weak gravitational fields, like those at the edges of galaxies. Instead, it tweaks the math so that the observed motions of stars and galaxies can be explained without needing invisible dark matter. Imagine gravity as a rubber band, stretching just enough to hold things together where Newton's equations say it shouldn't. One of MUND's biggest strengths is its simplicity. It offers a way to explain galaxy rotation curves without introducing an entirely new, undetected form of matter. Some galaxies even fit MUND predictions better than they do the dark matter model. But here's the catch: MUND struggles when it comes to larger cosmic structures like galaxy clusters or the cosmic web. Dark matter's gravitational scaffolding does a much better job at explaining how these immense formations hold together. Another hurdle for MUND is its compatibility with Einstein's theory of general relativity, which has been tested and confirmed in countless ways. While some versions of modified gravity try to bridge this gap, none have yet succeeded in fully replacing dark matter without creating new inconsistencies. So, is MUND a viable alternative? For now, the scientific community remains divided. While it offers an elegant solution in certain cases, dark matter still holds the upper hand in explaining the full picture of our universe. But that's the beauty of science. Every challenge to the status quo pushes us closer to the truth, whether it's hidden in the shadows of dark matter or in the fine print of gravity's laws. And speaking of hidden truths, our next stop takes us even deeper into the quantum realm, where dark matter might be tied to theories of supersymmetry and hidden dimensions. Now, let's venture into the strange and speculative world of quantum physics, where dark matter might be hiding secrets far stranger than we ever imagined. What if dark matter isn't just an invisible particle but a ghostly echo from another dimension or a hidden layer of reality? One tantalizing idea ties dark matter to supersymmetry, a theory that suggests every known particle has a heavier, unseen twin. These hypothetical particles, called superpartners, could include the elusive dark matter candidate neutralinos. If they exist, they'd be stable, electrically neutral, and barely interact with ordinary matter, making them perfect fits for the dark matter puzzle. But the quantum rabbit hole goes deeper. Some theories propose that dark matter could be a shadow cast by a parallel universe, one where gravity leaks into our own through hidden dimensions. Picture our universe as a sheet of paper. Dark matter might be the faint imprint of another sheet pressed against it, invisible yet shaping everything we see. Then there's the action, a feather-light particle born from quantum field theory. Unlike WIMP, actions would behave more like waves, rippling through space and only rarely bumping into ordinary matter. Experiments like ADMS are hunting for these phantom particles by tuning into what might be dark matter's faint cosmic hum. Could dark matter be the key to unlocking extra dimensions or even multiverse theories? While these ideas sound like science fiction, they're grounded in serious math and could explain why dark matter feels so alien compared to everything else we know. Whatever the answer, one thing's clear: dark matter isn't just a missing piece of our universe. It might be a doorway to a whole new frontier of physics, waiting to rewrite the rules of reality itself. And speaking of rewriting rules, our next stop takes us to a mind-bending possibility: stars that don't shine from fusion but glow with the eerie light of dark matter annihilation. Now, let's turn our gaze to one of the most fascinating what-ifs in cosmic history: dark stars. Imagine a star not fueled by the nuclear fusion that lights up our sun, but by something far more mysterious: the annihilation of dark matter. These theoretical giants could have been among the universe's first stars, glowing with an eerie, otherworldly light. Unlike ordinary stars, which shine by fusing hydrogen into helium, dark stars would draw their energy from dark matter particles colliding and annihilating within their cores. This process would release heat and light, but with a twist: their glow would be cooler and redder, a faint whisper compared to the blazing roar of fusion-powered stars. And their size, think colossal. Dark stars could have grown hundreds of times larger than our sun, even dwarfing the most massive stars we know today. Without the need for fusion, their growth wouldn't be limited by the same pressures that constrain ordinary stars. Instead of collapsing under their own weight, they'd balloon outward, sustained by the steady energy of dark matter annihilation. But here's the real kicker: if dark stars existed, they might still be out there, lurking in the cosmic shadows. Some theories suggest they could have collapsed into supermassive black holes, seeding the giants we now find at the centers of galaxies. Others speculate that remnants of these ancient behemoths might still drift through space, invisible to our telescopes but shaping the universe in ways we're only beginning to guess. So why haven't we found them yet? Their faint glow and cool temperatures make them incredibly hard to spot, especially across the vast distances of space. But upcoming telescopes like the James Webb Space Telescope might just have the sensitivity to catch a glimpse of these ghostly giants if they're out there. The idea of dark stars challenges everything we thought we knew about how stars live and die. And if they're real, they could rewrite not just the story of the early universe, but our understanding of dark matter itself. Up next, we'll explore another cosmic mystery, how dark matter might bend not just space, but time itself. Now, let's take a step into one of the most mind-bending questions about dark matter. Could it actually shape the flow of time itself? We know dark matter warps space with its gravity, bending light and sculpting galaxies, but what if its influence goes even deeper? Some theories suggest dark matter might not just bend space, it could twist time in ways we're only starting to imagine. Think of space-time as a fabric with massive objects like stars and planets creating dips in it. Dark matter, invisible yet everywhere, adds its own weight to that fabric. But here's where it gets wild. What if dark matter's gravity doesn't just create dips, but alters how time moves within those dips? In regions packed with dark matter, clocks might tick slower compared to emptier parts of the universe, an effect predicted by Einstein's theory of relativity. This idea isn't just science fiction. Some models propose that dark matter could form dense, invisible structures like rivers or walls where time flows differently. Imagine a spaceship flying through a dark matter halo. Its crew might experience time slightly out of sync with the rest of the universe. It's a subtle effect, but over cosmic distances it could add up. And there's another twist. If dark matter interacts with itself in ways we don't yet understand, it might create strange pockets where spacetime behaves unusually. Some physicists even speculate that dark matter could be linked to hypothetical particles or fields that directly influence time's arrow, though this remains firmly in the realm of theory. So why does this matter? If dark matter truly bends time, it could help explain mysteries like why some galaxies rotate faster than expected, or why certain cosmic structures seem to defy our models. It might even offer clues about the nature of time itself, whether it's a fixed backdrop or something more fluid, shaped by the invisible hand of dark matter. Up next, we'll shift gears and explore how dark matter has captured the imagination of storytellers, from blockbuster films to best-selling novels. The line between science and fiction might be thinner than we think. Now, let's step out of the lab and into the world of storytelling, where dark matter fuels some of the most imaginative tales ever told. From books to blockbusters, this mysterious substance has become a favorite tool for sci-fi creators, blending real science with wild speculation. Take Philip Pullman's His Dark Materials, where dark matter, or dust, isn't just cosmic glue but a conscious force tied to human souls. It's a poetic twist, far from the cold, invisible particles scientists hunt for, yet it captures the awe dark matter inspires. Then there's Interstellar, where the movie's black hole, Gargantua, warps time and space in ways that echo real physics, but the film also dances with the idea of hidden dimensions and unseen forces, nudging viewers to wonder, could dark matter be part of that unseen machinery? Sci-fi often exaggerates, turning dark matter into everything from alien fuel to portals between worlds. But here's the fun part, even the wildest stories get some things right. The way dark matter bends light, for instance, isn't far off from the gravitational lensing used in Interstellar to map distant planets. Games like Mass Effect take it further, with civilizations harvesting dark matter for FTL travel. In reality, we've got no proof dark matter could power engines, but the idea taps into a real scientific curiosity. What if we could harness it? That's the magic of sci-fi. It takes the sliver of what we know and spins it into what if, gold, pushing audiences to ask questions science is still trying to answer. But not all portrayals are created equal. Some stories treat dark matter like a hazardous mystery, a cosmic Pandora's box. Others, like the three-body problem, weave it into hard sci-fi, respecting its real role in galactic stability while still leaving room for fiction's flair. The best tales strike a balance grounded enough to feel plausible, but bold enough to let imagination soar. So why does this crossover matter? Because every time a movie or book gets someone curious about dark matter, it's a win for science. These stories are gateways, turning abstract equations into gripping adventures. And who knows, maybe the next big breakthrough will come from a scientist who first dreamed of dark matter in a theater or between the pages of a novel. Up next, we'll leap into the future, where dark matter isn't just a mystery but a potential energy source. What if tomorrow's tech could tap into the universe's hidden backbone? Let's explore. Now, let's shift gears and peer into a future where dark matter isn't just a cosmic mystery. It's the ultimate energy source. Picture this: advanced civilizations tapping into the invisible scaffolding of the universe, harnessing its power to fuel cities, starships, and technologies beyond our wildest dreams. It sounds like science fiction, but the theoretical possibilities are rooted in real physics. Dark matter's energy potential comes down to one key factor: density. Unlike ordinary matter, which clumps into stars and planets, dark matter is thought to be spread evenly throughout galaxies in vast, diffuse halos. If we could somehow capture and concentrate even a fraction of it, the energy yield would be staggering. Think of it like a cosmic battery. 1 teaspoon of dark matter could, in theory, contain more energy than thousands of nuclear power plants. That's because dark matter particles, if they interact weakly with ordinary matter, might annihilate upon contact, releasing pure energy in the process. Scientists have floated ideas like dark matter reactors, where controlled annihilation could generate clean, nearly limitless power. No greenhouse gases, no radioactive waste, just the universe's hidden fuel. Of course, we're light years away from making this a reality. First, we'd need to detect dark matter directly, then figure out how to trap and manipulate it. But the allure is undeniable. Imagine spacecraft powered by dark matter engines, zipping between stars without the need for bulky fuel tanks. Or megacities drawing energy from the galaxy's invisible halo, ending our reliance on finite resources. Here's the catch: dark matter doesn't behave like anything we've ever engineered. It doesn't emit light, absorb heat, or respond to electromagnetic forces, the usual tools in our energy toolkit. That means harvesting it would require entirely new physics, perhaps technologies that bend spacetime itself. Some theorists even speculate that dark matter could be linked to exotic phenomena like wormholes or quantum vacuum energy, opening doors to power sources we can't yet fathom. But let's ground this in what we do know. Dark matter's gravitational pull already shapes the cosmos. If future humans could somehow ride that gravitational wave, using it to slingshot ships or stabilize orbital energy grids, the practical applications would be revolutionary. It's a long shot, but history shows us that today's impossibilities are often tomorrow's breakthroughs. So while we're not building dark matter power plants yet, the dream is alive in labs and equations. And who knows, the same substance holding galaxies together might one day light up our future. Up next, we'll dive into an even wilder idea. Could dark matter harbor life itself? Strap in, this is where the cosmos gets truly strange. Now, let's venture into one of the most mind-bending questions of all. Could life exist within dark matter itself? Imagine a form of biology so alien, it doesn't rely on atoms, chemistry, or even light. Instead, it thrives in the invisible gravitational dance of the cosmos. The idea isn't as far-fetched as it sounds. If dark matter particles interact with each other in ways we don't yet understand, they could theoretically form complex structures, dark planets, dark stars, or even dark ecosystems. Picture a world where life doesn't need sunlight but is powered by the subtle tug of gravity or the annihilation of dark matter particles. These beings wouldn't see, touch, or communicate like us. Instead, they might sense gravitational waves or navigate through space-time ripples like fish in a cosmic ocean. Some scientists speculate that dark matter life could exist in halos around galaxies, invisible to our telescopes but woven into the fabric of the universe. Think of it like a shadow biosphere, a parallel web of existence right under our noses, or rather, right through us, since dark matter passes through ordinary matter effortlessly. Here's where it gets even stranger. If dark matter life exists, it would operate on timescales we can barely comprehend. Without electromagnetic interactions, processes might unfold glacially slow or blindingly fast. A single thought for a dark matter organism could take millennia, or their entire civilization might rise and fall in the blink of our cosmic eye. Of course, this is all speculative. We have zero evidence for dark matter life, and the very definition of life gets hazy when you remove chemistry from the equation, but the possibility challenges our assumptions. If life can emerge from something as elusive as dark matter, the universe might be far more inventive than we ever imagined. So while we search for microbes on Mars or signals from distant stars, remember the cosmos might be hiding its most exotic life forms in plain sight, or rather, in plain darkness. Up next, we'll tackle the ethical dilemmas. Should we even try to manipulate dark matter if we find it? The answers might surprise you. Now, let's shift our gaze to a question that's as thrilling as it is unsettling. What happens if we actually find dark matter? More importantly, should we dare to tinker with it? The moment we detect this elusive substance, we're faced with ethical dilemmas that could redefine our relationship with the cosmos. Imagine harnessing dark matter as a tool or energy source. The possibilities sound like science fiction: dark matter reactors, gravity-based technology, even cosmic engineering on a galactic scale. But here's the catch: we have no idea what unintended consequences might follow. Dark matter isn't just some inert backdrop of the universe. It's the scaffolding holding galaxies together. Mess with it, and we could destabilize the very structures that allow stars, planets, and life to exist. Think of it like pulling a single thread from a tapestry. At first, nothing seems to happen, but what if that thread was anchoring the entire design? Dark matter's gravitational influence is so vast that even small manipulations could ripple across millions of light years. Could we accidentally unravel a galaxy's rotation? Disrupt the cosmic web. The risks are as enormous as they are unknown. Then there's the philosophical side. If dark matter does harbor exotic life, as we speculated earlier, would manipulating it be ethical? We'd be meddling with a potential ecosystem we can't even perceive, like bulldozing a rainforest we're blind to. The universe might have rules we don't understand, and breaking them could have consequences we can't foresee. Of course, curiosity and innovation have always driven humanity forward. The same questions were asked about splitting the atom or editing genes. But dark matter operates on a cosmic scale, and mistakes here wouldn't just affect a lab or a city, they could echo across the universe. So where does that leave us? Proceed with caution or embrace the gamble? One thing's certain: the debate over dark engineering will force us to confront not just the limits of our knowledge, but the weight of our responsibility as a species. Up next, we'll explore the flip side. What if, after decades of searching, we've been wrong all along? The story of dark matter's most stubborn mysteries is just ahead. Now let's take a step back and look at the other side of the search, the experiments that didn't find anything at all. Science isn't just about breakthroughs. It's also about dead ends, unanswered questions, and the stubborn mysteries that push us to think differently. For decades, scientists have set up detectors deep underground, scanned the skies with powerful telescopes, and smashed particles together in colossal colliders, all hoping to catch even a whisper of dark matter. Yet, time and again, the results have come up empty. Experiments like LUX Zeppelin and Xenon 1T, designed with incredible precision, have found no definitive trace of dark matter particles. Even the Large Hadron Collider, which discovered the Higgs boson, hasn't produced any signs of dark matter. But here's the thing, failure in science isn't really failure. Every null result narrows down the possibilities, forcing researchers to refine their theories and rethink their approaches. It's like solving a puzzle where every wrong piece you try helps you understand what the right one must look like. When one path closes, another opens. The absence of evidence has led physicists to explore alternative ideas, from lighter particles like actions to entirely new theories of gravity. This is how science moves forward. Each experiment, whether it succeeds or not, adds another piece to the grand puzzle. The hunt for dark matter has taught us just as much about what it isn't as what it could be. And that's the beauty of the process. Every unanswered question is a stepping stone to a deeper understanding. So while we haven't found dark matter yet, the search itself has reshaped physics in ways we couldn't have predicted. And who knows, the next experiment, the next idea, might finally crack the mystery wide open. Up next, we'll tackle some of the biggest misconceptions about dark matter, because in a field this mysterious, myths are bound to take hold. Now, let's clear up some of the wildest ideas floating around about dark matter. When something is this mysterious, it's no surprise that myths and misconceptions start to creep in. So, is dark matter secretly dangerous? Could invisible aliens made of this stuff be lurking in the cosmos? Let's tackle these head-on with a little humor and a lot of science. First up, the fear that dark matter might be harmful. The truth, it's about as dangerous as a ghost that can't even rattle a chain. Dark matter doesn't interact with light or ordinary matter in any meaningful way. If a dark matter particle passed through your body right now, you wouldn't feel a thing. It's like worrying about being hit by a snowflake in a blizzard, except the snowflake doesn't even touch you. Then there's the idea of invisible aliens. Sure, it sounds like the plot of a sci-fi thriller, but here's the catch. Dark matter doesn't form atoms, molecules, or anything complex enough to build life as we know it. No DNA, no cells, no tentacles, just particles that barely notice each other. Even if some clever extraterrestrial evolved to interact only gravitationally, they'd have a hard time building spaceships or plotting invasions when they can't even hold a wrench. And let's not forget the classic, dark matter is just undiscovered black holes. While black holes are undeniably cool, they're not the answer here. We've looked hard. If dark matter were made of black holes, we'd see their gravitational effects everywhere, bending light in ways that just don't match observations. Sometimes the simplest explanation isn't the right one, and in this case, the universe is playing a much weirder game. The bottom line, dark matter isn't out to get us, and it's not hiding intelligent life, at least not in any way we'd recognize, but that doesn't make it any less fascinating. The real mystery is why the universe is built this way, and that's a puzzle worth solving. Next up, we'll explore how you can actually join the hunt for dark matter. No lab coat required. Now, here's something truly exciting. You don't need a fancy degree or $1 billion lab to be part of the dark matter hunt. Believe it or not, you can contribute to cutting-edge science from the comfort of your couch. Citizen science projects have opened the door for everyday people to help researchers sift through mountains of cosmic data, and some of them are zeroing in on dark matter. Take Zooniverse's Dark Matter Explorer, for example. This online platform lets volunteers analyze real telescope images to spot gravitational lensing effects, those subtle distortions in starlight caused by dark matter's gravity. It's like a cosmic version of Where's Waldo, except instead of a striped sweater, you're searching for invisible mass warping the fabric of space. Scientists simply don't have enough eyeballs or time to process all this data alone, so they're crowdsourcing the effort. And guess what? Amateurs have already made genuine discoveries, helping map dark matter in ways computers alone can't. But that's not the only way to get involved. Projects like Einstein at Home use your computer's idle processing power to scan for faint signals in data from radio telescopes, hunting for clues about dark matter's behavior. It's like turning your laptop into a tiny piece of a global supercomputer. Even if you're just clicking through galaxy images or running calculations in the background, you're part of the team pushing the boundaries of what we know. The best part, you don't need any prior experience. These projects come with tutorials, friendly communities, and the thrill of knowing you might stumble on something no one's ever seen before. So why not give it a shot? The universe's biggest mystery could use a few more detectives, and who knows, the next big breakthrough might have your name on it. Up next, we'll dive into an even wilder idea, using dark matter as a gravitational slingshot for intergalactic travel. Buckle up. Now, let's take this idea even further. What if dark matter isn't just something we study, but something we could actually use? Picture this: future civilizations harnessing the invisible pull of dark matter to fling spacecraft across the cosmos. It sounds like science fiction, but the physics behind it might just hold up. Think of dark matter halos, those massive invisible clouds surrounding galaxies as cosmic highways. Just as surfers ride ocean waves, advanced spacecraft could theoretically surf the gravitational tides created by dark matter. By carefully navigating these halos, a ship could gain speed without needing massive amounts of fuel, using dark matter's gravity as a natural slingshot. This isn't just wild speculation. We already use gravity assists from planets to boost probes like Voyager and New Horizons. Dark matter halos, being far more massive, could offer an even bigger push. Imagine a future where ships plot courses through the densest patches of dark matter, slingshotting from one galaxy to another. The Milky Way's halo alone stretches hundreds of thousands of light years, plenty of runway for an interstellar speed boost. Of course, there are hurdles. We'd need to pinpoint dark matter's exact distribution, something we're still figuring out, and building tech that can withstand such extreme gravitational forces. That's another challenge, but if we crack it, dark matter could be the key to unlocking intergalactic travel, turning a journey that would take millions of years into something far more manageable. So, could we one day ride dark matter's invisible waves? The possibility is as thrilling as it is daunting. Up next, we'll step back and reflect on what all this means for our place in the cosmos, because dark matter doesn't just shape galaxies, it might reshape how we see reality itself. Now, let's take a moment to step back and consider what dark matter teaches us about the universe and ourselves. It's a humbling thought. Everything we see, from stars to galaxies, makes up just 5% of the cosmos. The rest is hidden in plain sight, invisible yet shaping the very fabric of reality. This isn't just a scientific revelation, it's a cosmic wake-up call, reminding us how much we still don't know. Think about the Copernican revolution, when we realized Earth wasn't the center of the universe. That shift didn't just change astronomy, it shattered our entire worldview. Dark matter is doing the same today. It's forcing us to confront the idea that the universe operates in ways we can't even perceive directly. Just as Copernicus showed us we weren't at the center, dark matter reveals that what's visible is just the tip of the iceberg. And this isn't the first time science has humbled us. Every major discovery, from quantum mechanics to the expanding universe, has peeled back another layer of reality, showing how much lies beyond our senses. Dark matter is the latest chapter in that story, a reminder that the universe is far stranger and more mysterious than we ever imagined. So what does this mean for us? It's an invitation to stay curious, to keep questioning. After all, the greatest breakthroughs happen when we admit what we don't know. Dark matter isn't just a puzzle for physicists, it's a metaphor for the hidden forces shaping our lives, both in the cosmos and here on Earth. The more we learn, the more we realize how much is still out there waiting to be discovered. And with that, we come to the end of our journey, but not the end of the story. Because when it comes to dark matter, the universe still has plenty of secrets left to share. As we wrap up this cosmic journey, let's take one last look at the incredible story of dark matter. This invisible substance isn't just a scientific curiosity, it's the hidden architect of the universe, holding galaxies together and shaping the cosmos on the grandest scales. Without it, the night sky as we know it wouldn't exist. The hunt for dark matter is one of the most thrilling detective stories in modern science. From deep underground labs to space telescopes scanning the heavens, researchers are piecing together clues that could rewrite the laws of physics. Every experiment, every observation brings us closer to unraveling this cosmic mystery. But here's the most exciting part: we're still just scratching the surface. Dark matter reminds us that the universe is full of surprises, waiting for curious minds to uncover them. Whether you're a scientist, a stargazer, or just someone who loves a good mystery, this is your invitation to keep exploring. So stay curious, stay amazed, and remember the universe's greatest secrets are still out there, waiting. If you enjoyed this deep dive into the invisible forces shaping our cosmos, don't forget to hit that like button, subscribe for more mind-expanding content, and ring the bell so you never miss an adventure into the unknown. Until next time, keep looking up.